Hello everyone, today we'll discuss chapter 11. The title is Pollutant Formation and Control. This is the content of chapter 11. The first subtopic is nature of pollutant formation in internal combustion engines. And then we'll discuss one by one each type or each species inside the pollutant of internal combustion engine. The first one is nitrogen oxides or NOx, and then carbon monoxide CO, unburned hydrocarbon UHC, and then particulate. And the last subtopic is about the exhaust gas treatment to reduce the pollutant formation in internal combustion engines. As has been discussed in the previous chapters, spark ignition and compression ignition engines are major sources of air pollutant. This is through the burn gas that exit the engine through the exhaust system. In the spark ignition engine exhaust gases, it can contain several burn gas species. Some of these are air pollutant. The first one is oxides of nitrogens. This consists of nitric oxide, NO, and NO2, so nitrogen dioxide. Both species are collectively known as NOx. Okay, so this NOx is the sum of NO and NO2. In spark ignition engine, the dominant species for this NOx is NO. The next one is carbon monoxide or CO. This is a toxic pollutant. And then we also have organic compound, which are reacted or partially reacted fuel hydrocarbon. So it's called unburned hydrocarbon. It can be CH4 or any lower C number species. And then the relative amount of this engine out emission that enters the exhaust depend on the engine design and operating condition. For example, if we have rich mixture combustion, we might have a dominant CO and unburned hydrocarbon. Conversely, if we have lean mixture combustion, we might have higher NOx but smaller amount of CO and UHC. This is a rough estimation of the pollutant amount in internal combustion engine. For example, NOx we might have between 500 to 1000 ppm, or it's equal to 20 gram per kilogram fuel. CO can be between 1% or around 1%, or it is equal to 150 gram per kilogram fuel. And then hydrocarbon, it is around 2000 ppm. This is as a C1, or 15 gram per kilogram fuel. Other pollutant that might came up from this spark ignition engine is blow-by gas. This blow-by gas can consist of, for sure, air and then unburned fuel, okay, or maybe burn gas, depending on which timing we have this blow-by gas. But in the modern spark ignition engine, we usually have what is called closed crank ventilation, so which means that this blow-by gas is rerouted back to the intake system. In diesel engine exhaust gas, we have NOx that is comparable to that from spark ignition engine. There is also hydrocarbon emission, although it is lower due to better combustion efficiency. So we have lean mixture combustion process in the diesel engine that result in higher combustion efficiency than that for the spark ignition engine. The hydrocarbons in the exhaust may also condense to form white smoke during engine starting and warm up, and this is the source of diesel odor. Diesel engines are also an important source of particulate emission. So this is a unique exhaust gas emission for diesel engines. So in this case, between 0.2 to 0.5% of the fuel mass is emitted as a small particle. So small particle with the size between 10 to 500 nanometer in diameter, and this is a soot, and it has also additional hydrocarbon in it. Diesel engines are not a significant source of carbon monoxide, and this is primarily due to Lin's mixture combustion. Other pollutants that might be generated inside an internal combustion engines are aldehyde. So this become a significant contributor to the photochemical smoke, and this is generated when we have oxygenated fuel, so like gasoline plus 10% ethanol or E10. So when it is plus 15% ethanol, then we have E15. The next one, that the dominant fuel, gasoline and diesel, can contain sulfur, okay, and this can vary depending on world region, and this sulfur will be oxidized or burned to produce sulfur dioxide or SO2, and some of this will be further oxidized to form a sulfur trioxide or SO3, and this SO3 combines with water to form a sulfuric acid aerosol. Sulfur over time degrades the effectiveness of the exhaust catalyst, okay, and we have several exhaust after treatment systems that use catalysts like SCR, selective catalytic reduction, to reduce the NOx emission. We also have three-way catalysts that reduce the amount of NOx, unburned hydrocarbon, and CO. This picture is showing the schematic of pollutant formation process in the spark ignition engine. The picture on the left is showing the process during the compression stroke. So the piston move up toward TDC, and then there will be an unburned fuel flowing into the crevice, so into this one, okay. And then during this period, the oil layer on the liner will absorb hydrocarbon, which is the fuel. Okay, there will be also hydrocarbon absorption by a deposit that is attached to the cylinder head. And then during the combustion process, because of increased cylinder pressure, increased pressure around this region, there will be unburned gas flow into the crevice, as showing here, as well in this one. And then inside the burn zone, there will be a formation of NO, okay, and this is mainly due to the high temperature condition. There will be also a formation of a CO if we have a fuel-rich mixture combustion, and this will be formed inside the burn zone. And then the end gas, which is ahead of the flame front. So let me put red here to show the flame front. So this is the flame front. So the burn gas, so this one, this blue region, is also source of the hydrocarbon pollutant if we have incomplete combustion, okay. And we will also have a burn gas flow into the piston crevice, if any. The next schematic on the left is the process during the expansion stroke. So at this time, the piston moves down toward bottom center, and the chamber volume increases, and thus the pressure decreases. So there will be a pressure decrease in this zone that will result in the backflow from the crevice into this main chamber, and depending on the temperature level of the chamber at the time of this backflow, some of this unburned hydrocarbon might be burned, or some of these might stay alive throughout the remaining process in the chamber and thus will be the source of the unburned hydrocarbon. Another process that we might have here is that as the burn gases cool, first NO chemistry, then CO chemistry freezes. What is the implication of this is that the NO and CO won't be converted into other species. So we will have CO and NO throughout the remaining process inside this chamber and will be the source of NO and CO pollutant. Some of the hydrocarbon might burn up on the wall, once again depending on the temperature level around the wall. Also, outflow of the hydrocarbon from crevice here might also burn around the wall. And then the next schematic on the right side here is showing the process during the exhaust stroke. So the piston move up toward top center, and there will be a hydrocarbon scrap along the wall by this piston movement, and this will be the source of the unburned hydrocarbon. And then the oil layer that absorb hydrocarbon during compression stroke will dissolve hydrocarbon, and this will be also the source of the unburned hydrocarbon. The next one is that deposit will also dissolve hydrocarbon. So all of this hydrocarbon will exit through this exhaust system and will be the source of the unburned hydrocarbon. This figure is showing the variation of hydrocarbon HC and then a CO, and then this one is NO. Let me put it on here. This one is NO for the spark ignition engine. So this is a function of equivalent ratio. As you can see on this figure, as we increase the fuel air equivalent ratio, so it means we have a richer mixture, the amount of HC and CO pollutant increases. So you can see from this one. And then the NO emission has a maximum level at the phi around 0.9. So you will see later on that the NO emission is controlled by the temperature level. So which means the maximum temperature will be, the maximum combustion temperature will be around stoichiometric condition here. Okay, this NO emission is also governed by the amount of air. Okay, so having more air, so it means having a leaner mixture, will increase the NO emission. However, as we have a leaner mixture combustion, the combustion temperature decreases. So this is the point where the NO is maximum. It is at the phi around 0.9. Next one is the pollutant formation process in the compression ignition engine. As you have learned in chapter 10 that we have non-premix combustion process in the compression ignition engine. The combustion process period can be split into two periods. The first one is what's called premix period, that is followed by mixing control period. And this premix period occurs right after the ignition delay period. In the premix period, there might be a soot formation. Okay, it is inside the spray, and then there might be also hydrocarbon formation in the lean flame out region here. There might be a noise as well because of the initial rapid combustion, and then because of huge momentum difference between the spray and surrounding air, there will be an air entrainment inside this spray as well. And then in the mixing control period, there will be unburned hydrocarbon formation on the wall because of the flame quenching, and there will be also NO formation inside the flame front, and then in the rich zone in the fuel jet, so it is inside the spray, there will be a soot formation, and then on the periphery of the spray there will be soot oxidation that will reduce the final formation or the final production of the soot. And then on the sac volume of the injector, there might be a fuel vapor that will be a source of the unburned hydrocarbon. Okay, we have a look at the formation process of the pollutant inside the internal combustion engines. Next topic is looking at individual pollutant. So the first one here is the nitrogen oxides or NOx. So this is the sum of NO and NO2. Once again, NOx here is the sum of NO and NO2. And the predominant oxide of nitrogen is NO. This is the principal reactions governing the formation of NO from nitrogens. So we have three reactions here. So on the first reaction, we have N2 react with a single O to produce NO and N. And then the next reaction here is single N plus O2. And then the product is NO and O. And then the next one is N plus OH. The product is NO and single H. And we have equal sign on these three reactions, which means that this reaction can go in both directions. It can go to the right, it's called a forward reaction, or it can go to the left, it's called a reverse reaction. And this direction is controlled by the thermodynamic condition inside the chamber. So from the three reactions, we can use the chemical kinetic to estimate the formation of NO. We will have equation 11.4. So this is the formation of NO from reaction 11.1. This is from 11.2, and this one is from 11.3. K here is the reaction constant. It is with the upper sign here of plus. It means that this is for forward reaction. And then it is subtracted by the reverse reaction, because if you have a reverse reaction for example, from equation 11.1, you will have a consumption of NO. So NO will reduce. Therefore, we have a negative sign here. Similarly, this is from the reverse reaction of second reaction. This is the reverse reaction of the third reaction. And this table 11.1 is showing us the amount of the reaction rate constant. And this is a function of temperature. And this is the range of the condition for this reaction rate constant along with the uncertainty factor or the percent error here. NO forms in both the flame front and the post-flame gases. And because the combustion process occurs very fast, it has a very small time scale, while we have a large time scale for the post-flame condition. We can decouple the NO formation between the flame front and the post-flame. So in this case, it is appropriate to assume that the combustion chemistry and NO formation processes are decoupled. When we assume this, then we can have or we can apply an equilibrium process for the NO formation, and we can simplify the kinetic reaction in the previous slide to have a simple one following this equation 11.7. So this one is another formula assuming that the NO formation is under equilibrium condition. Okay, and table 11.2 here is showing the amount of the several parameters in the equation, like the R1 plus and then R1 over R2 and so on. NO formation depends strongly on temperature, so we can use a previous equation in the previous slide, so equation 11.7, to get the correlation between the NO formation and temperature. So by applying several assumptions, we will get equation 11.11. So in this case, you will see that the NO formation is a function of temperature. Okay, and this feature is showing the NO formation as a function of temperature. So it is in the horizontal axis. You can see in here that for any phi number that the NO production increases with the temperature increase. Also with a linear mixture, so in this case you have a smaller phi, the NO formation also increases. So in this case you see that the NO is strongly a function of temperature and the amount of air. The next one is NO2. NO2 over NO is slow in spark ignition engine, but it can be 10 to 30% of the total NOx in diesel engines. This NO2 is formed from the conversion of NO that is formed in the flame zone following this equation 11.14. So we have NO and then react with HO2 to form NO2 and OH. Subsequently, this NO2 production will be converted back to the NO following equation 11.15. But from both reactions, we might have some NO2 at the end. This feature is showing an example of NO and NO2 emission data from a spark ignition engine on the left side and a diesel engine on the right side. First, take a look on the left side. So we have NO. So this is the first vertical axis, and NO2 on the second vertical axis. So this one is the solid line for NO and then dash line for NO2. And this is a function of air-fuel ratio. So they are maximum at certain air-fuel ratio. Okay? And for example, if we look at certain point air-fuel ratio, let's say 15. So in this case, we have a very low NO2 to NO. So it might be around 2%. And then on the right side, we have the NO2 over NOx as the vertical axis. And this one is a function of engine load at different engine speed. So as you can see in here, we have a much higher NO2 over NOx compared to the one for spark ignition engine. For example, at light load, so we have the highest NO2 over NOx, so it is around this one. So this one is the area where the NO2 over NOx is higher, and for sure it is also depend on the engine speed as well. This is the most important engine variable that affect NO emission. So we have a relative air-fuel ratio, and then the burn gas fraction of the in-cylinder unburned mixture, and then spark timing, and the next one is fuel properties. The burn gas fractions depend on the amount of diluent, such as recycled exhaust gas or EGR, that is used for NOx emission control, as well as the residual burn gas fraction from the previous cycle. This feature is showing the variation of exhaust engine out NO concentration with the air-fuel ratio and a relative air-fuel ratio, or lambda. So the maximum here occurs at lambda around 1.1, so it means it is slightly lean mixture. So as we increase lambda, so we have more air, which increase the amount of NOx. But at the same time, we have a lower combustion temperature, which decrease the amount of NO. Therefore, the maximum point is somewhere here. So similarly, if we make the mixture richer, so we will have lower NOx due to less amount of air, but we have a higher combustion temperature which increase the NOx. So this is the maximum point where the NOx is formed inside the spark ignition engine. And this data was obtained at 1600 RPM and then MPT timing with the volumetric efficiency of around 50%. This picture is showing the variation of exhaust engine out NO concentration as a function of the EGR percent. We have three lines here showing a different air-fuel ratio. As you can see in this feature that we have substantial reduction of NO with the increase of EGR. And this strategy is currently used in the engine to reduce the NO formation inside the internal combustion engines. And the primary effect of this NOx reduction by having the burn gas diluent is that it reduces the flame temperature by increasing the heat capacity. The feature on the left side here is showing the reduction in mass for NO, and this is a function of a diluent in the intake in percent volume for a different diluent. So we have a CO2, H2O, and this one is typical exhaust gas. We have N2, He, helium, and this is A. I think this is Ar. As you can see in this feature that CO2 and H2O have the highest impact on the NO reduction, and this is because of the highest Cp compared to the other diluent. So if you have, let's say, higher CO2 inside the burn gas, you will have a better NOx emission compared to the one with less CO2. But unfortunately, we cannot control this CO2 amount in the burn gas. So it is the result of the combustion process, and the CO2 is usually within a certain range. And then on the right side, it's showing the reduction in mass for NO, and this is a function of a diluent heat capacity. Now you have a single line here showing a good correlation between the NO formation to the diluent heat capacity. Spark timing has an impact to the NO production. This figure is showing the variation of the exhaust engine out NO concentration with the spark timing. As we advance the spark timing, the combustion pressure and combustion temperature increases, and thus increases the NO production. As you can see in here that the NO increases with advanced spark timing. Next one is NOx in the compression ignition engine. Almost all the NO will form in the mixing control diffusion flame burning process. This figure is showing the schematic of NO formation in the diffusion flame sheet surrounding each diesel fuel spray. So the horizontal axis here is the distance across the flame sheet. So it means that right at this vertical axis, this is the flame front. Okay, so this is the flame front. So on the left side, it is inside the spray. On the right side, it is outside the spray. Therefore, as you can see in here, as we go to the right, we have an increase of the oxidizer concentration, which means it is inside the spray, so we have more air. And then we also have a decrease of temperature, so the temperature is maximum at this flame front. Okay, and then the NO concentration is maximum at this flame front as well. So this is where the NO is formed, and then it decreases as it's moved away from the flame front. So this dot line, and then this is the excess NO production. So it's also maximum around or close to the flame front location, and this is the bulk NO production, which is small compared to the one close to the flame front location. This picture is showing the NO and NOx concentration as a function of equivalent ratio or a function of engine load. As you might know that the diesel engine load is directly controlled by the fuel amount. You can fix the airflow and then you can increase the fuel amount to increase the load. So up to 0.7, we saw an increase of NOx and NO. If you remember in the previous slide that the maximum NOx occurs around phi of 0.9. This figure is showing the effect of reduction in oxygen concentration by different diluent on the left side. So we have a CO2, we have a typical exhaust gas composition, and we have N2. So as you can see on this feature that the NOx amount decreases with the increase of the diluent amount. And then on the right side is showing the effect of recycled exhaust gas EGR at a light load and then mid load and high load. So on all load levels, NOx emission here decreases with the increase of EGR percent, and the effect of diluent is high when the engine operated at a higher engine load.